chapter N, the natural logarithm. And we want to be able to take the derivative of the natural logarithm. Now, the natural logarithm follows from the natural exponential function, y equals e to the x, where e is our natural base. Now, the definition of the log with respect to a given base, like for example, if you had y is equal to some base to a power x like this, then we would say the log of y, and this would be base b, would be equal to x. So we want the log of y base e, but since that's the natural one, we have our notation ln for that. So we could have written log with the little e, but that is defined to be ln. So the natural log of v to the x, you have just x, like that. All right, so we want to do the derivative. Now we're going to remember from the last class that we know the derivative of e to the x dx is equal to e to the x. We know that from the last class. And we also know from the last class that e to the x is equal to the limit as n goes to infinity of 1 plus x over n to the nth power. So these are going to be handy in this chapter. So what about this inverse function? Well, remember for inverse functions, we have our trick where we're going to look at a reflection. And go ahead and put in a few things here, like this. So this is x, and this is, say, e to the x along this axis. When we have x is equal to 1, we would have e. And e is 2.7, so e is up here somewhere. When x is 0, you have 1. So it's going to go up like this. We have our y equals x mirror for the reflection. Then here we would have this point corresponding to that point. And when we go, say, to the point where we have almost 3, when you have e to the 1, it's almost 3. Almost 3 here, nice reflection. Here would get us, about, I'm going to eyeball it, about there. So this is going to be the log of x. And then here, when you have a negative value for x, this starts heading toward 0 as you get larger and larger. And if you had -1, say here's -1, you'd have 1 over e. E is almost like 3, so that's like 1/3. That would be like about there. This is just a sketch to get an idea of what the graphs look like. So this one here, when you go here by the reflection, you go 1, 2 that way, 1, 2 that way, then we're kind of like a lot like this. All right, and just a sketch. So remember that when you have a mirror, when you stand in front of the mirror, your reflection has an image that's the same distance on the other side. So we're trying to find the slope of this log of x. That's the slope, the derivative. So here we're going to look at 3 ways to do this. I like doing things more than one way. Richard Feynman, a theoretical physicist, gave a talk at Cornell in 1964, and he said that every good theoretical physicist should, quote, know 6 or 7 different theoretical representations for exactly the same physics and know that they're all equivalent, quote. So here I'm going to use 3 approaches, 3 methods to find the derivative of the natural log of x. So we'll do method 1 first. And method 1 is going to be our inverse function trick, where we have, say, go ahead and I'll just say this is our usual approach, the inverse method. I'll just call this the inverse method that we have done before. Now for the inverse method, you have a function y that's equal to, say, f of x, and that's going to be e to the x. And then we have the inverse function x is equal to some g of y. And you could write that as an inverse function of f, but I like to use g because I think that's a little confusing, at least to me. And I like to just remember that g is the inverse function. To go the other way, you put in the y and you get the x. Then we had our rule that the derivative of the inverse function with respect to its argument is equal to 1 over the derivative of the function f of x with respect to its argument. And you could write that in an abbreviated form, like, say, g prime of y is 1 over f prime of x, like that. So that's what we're going to do here. So the derivative of the natural log of y with respect to y is 1 over the derivative of the f of x function, which is e to the x, with respect to x. And that's going to be the same thing. So we're going to have 1 over e to the x. Then we remember that e to the x is y, so we can write this as 1 over y, and we're finished. The last step, what I like to do is replace the y with another variable, a new x. In other words, forget all the definitions above and just say this is true if you have u here and a u there, a z there and a z there. So I like to give the final equation as the derivative of log of x is 1 over x. And that's our final result. I'd like to do that in 2 more different ways. So the next step we'll call method 2. I'm going to nickname method 2 chain rule. Chain rule method. Now, for this method, what we're going to do is the approach that most people will do is they will start with a new definition of x's and y's and just call the y here equal to the natural log of x. Now remember the notation that we used over here, we called y e to the x. So I'm going to have new notation here and start with y equals the natural log of x. So I want to take the derivative of this. And that's the approach that you'll usually see when this method 2 is used. So that means that here x is equal to e to the y power. So if I take the natural log of x, I simply have y. So now we're about to do the problem by taking the derivative of this equation with respect to x. So I have dx is equal to d dx of e to the y. And now we use the chain rule. This one's going to be d e to the y with respect to y, and then dy dx. That's why we nicknamed that the chain rule one. Now notice here, two neat things. This is 1. The derivative of x with respect to x is 1. And this gets us back the same thing. This is the derivative of e to the y with respect to y is simply e to the y. Now, we can look at this as giving us a 1 on the left side equals e to the y dy dx. But dy dx is what I'm interested in. That's the derivative of the natural log of x. And that's going to be 1 over e to the y. So I have my result. The derivative with respect to x of the natural log of x is equal to 1 over x, which we already have found. Now we're ready for method 3. And for method 3, I'm going to say the derivative formula. So for the derivative formula, we have the derivative of the function f of x is equal to the limit as h goes to 0 of the function at x plus h minus f of x, that's our rise, and over the run is h. So we're going to use this where the function f of x is equal to the natural log. All right, so let's do that. The derivative of the natural log, and I'll put the x in parentheses here, dx is equal to the limit as h goes to 0 of the function natural log at x plus h, and then subtract the natural log at x divided by h. Now when you have the logarithm, say, of a minus the logarithm of b, then we can write that as a logarithm of a over b, so that's what we're going to do next. So I have here the limit as h goes to 0 of logarithm x plus h over x, and there'll be a 1 over h there. So we do something like this here. Okay, and when you have the logarithm of something with an exponent, you pull that exponent down. So for example, if you wanted the logarithm, say, of, say, a to the b power like this, you would have the b would come down, and you would have then the log of a. So we're going to then do that backwards. We're going to start with this and then put the b up in the exponent. So we have the derivative of the natural log with respect to x, and that's going to be the limit of h going to 0 of the log x plus h over x, and we have then the 1 over h up there. And let's go ahead and divide by the x. And if we do that, we'll have the limit as h goes to 0 of the natural log of 1 plus h over x to the 1 over h power, like this. All right, now, when we talked about limits earlier, we said that if we have the limit on the outside like this, we could say this is going to be able, we'd be able to move this inside and have the log of the limit. Now, I'm not proving that. You would see that proof in a course on calculus, but remember we said that these seem reasonable to have something where, let me go ahead and show you in general what I'm talking about here. Say if you have the limit as x goes to a of f of x, what we're saying here, that would be the same as f of the limit as x goes to a, and we have then x like this. In other words, we move the limit inside, and that is reasonable. That is a reasonable thing. For example, if we had f of x is equal to the sine of x, and say we want to let x slide to a, then here, if I looked at this form, I would have the sine of x, and let's go ahead and say a is 30 degrees, all right, or pi over 6. So the sine for 30 degrees could be 1/2. So here I would say this is the sine of 30 degrees, which is 1/2. And then over here I would say, well, I'm going to let x slide to 30 degrees first, and then take the function, which is the sine of 30 degrees. So you see, for a physicist, we'd not worry about that. This seems so reasonable. It seems obvious, but it's technically not obvious. It needs to be proven from the mathematical, rigorous point of view. So I'm going to be careful here, not worry about that, because as you can see here, it works out very, very, very easily. Let me give you an example that won't work. So we're going to check out here the limit as x goes to a of f of x, and I'm going to show you a case where these are not going to be equal. Now we're going to use the sine of x as an example, and I'm going to look at a to be pi over 6, 30 degrees, so that the sine of pi over 6 is 1/2. But the sine does something like this. All right, and this is here pi over 2, and this is 1, and if we go up 1/2, we're at pi over 6. So that's the sine of x. But now what I want to do, here is have a different function that is just like the sine. This is going to be the f of x function, just like the sine, so they overlap. But at this point, it's up here, there's a gap. There's a gap right here, I put a little circle, a little gap. And the value of our function, so our function, f of x, is going to be exactly like the sine of x. You might say that f of x is equal to the sine of x as long as x is not equal to pi over 6. But it's equal to 1 if x equals pi over 6. So that's my function. So now, as I look at, say, the limit as x goes to a, pi over, let's say pi over 6 of f of x, here's f of x and some arbitrary x value, but as I let this limit as the limit of f of x as x goes to pi over 6, I kind of slide down here. Or if I go the other way, I slide up here, and the limit is going to be 1/2. It's going to be a gap there, but that's going to be the limit. However, if I, at first, let the x slide to pi over 6 and then put it in the function, I get 1. So you might say, well, this is crazy. Well, yes, it is. And see, that's why we don't worry about this in physics and engineering, because we work with good functions that are continuous. We just assume that. So for all the functions that we're looking at, these limit rules will apply. So here, what we're going to do is simply move it in. We're going to move that limit inside, and we'll have here the logarithm, and we put the limit on the inside. We'll have, say, here the logs on the outside, then the limit is going to go in. So here's the limit as h goes to 0 of 1 plus h over x 1 over h. All right, so we've moved it in. All right, now I'm going to make a couple substitutions here, because I know that e to the x is equal to the limit as n goes to infinity of 1 plus x over n to the nth power. So what I would like to do is I would like to let u be 1 over x and let n be 1 over h. All right. So this way, 1 over x, I can put the u in there, and then here, this also is saying that h is 1 over n. So when I make those substitutions, I need to remember that when the h goes to 0, the n is going to go to infinity. So then I'll have the log of x like this, dx, and I'll have the natural log outside. And now here, I'm going to have the limit as n goes to infinity, 1 plus, and see the h is 1 over n, and the 1 over x is u. So this will be equal to u over n. And this is then to the nth power here. All right, let's look at that one more time. H is going to be 1 over n. So there's the 1 over n is there. 1 over x is u. And then 1 over h is n. Okay, now that when I have this, I see that I could identify x with the u and the n is there. So this is going to be equal to, when I take this limit, this is going to be simply e to the u. Now when I take the logarithm of e to the u, this is going to be u. You could write it out like this, then the log of e using the general formula, but see the log of e is 1. This is going to be u. So if you take the natural log of e to some power, simply that power. So that means the derivative of the natural log with respect to x like this is equal to u, but u is 1 over x. This is 1 over x, and we have the answer a third way. This is marvelous to be able to see 3 derivations of the derivative of the natural log.